This conference will now be recorded.
Okay, so today what I wanted to talk about is a concept called templates. Now, one of the things that we've been doing in Visual Sim and we've been doing very well is creating library blocks. So blocks of like processors, memories, stochastics, traffic, things like that. What we have not been good at, though we have created some, what we've not been good at is really promoting templates. So what are templates? Templates are emulating a particular sequence that refers to an application. So for example, if I go into a very detailed template here, this one here represents a pulse Doppler and a scatter radar system. You can see from the time that the data is acquired, it goes through a sequence of things, and finally you have either the movement tracking or the static tracking indicators that are the other end to tell you exactly what is going on in the system. Now, this one here is an extremely accurate model, and I'm not going to go explain this one right now. I'll explain this in a separate session. But just to show you that a template, if you had one of these, someone that's building a radar system could take this flow, create their own hardware model. In this case, they've got a hardware model with a PCI and two DSP clusters. Yeah.
Are you sharing the screen?
Ooh, I forgot. Let me start again from scratch. Thanks. Okay, so can everybody see my screen?
Yes, now I can.
Yeah. Okay. Okay. So let me get started. So today what I'm going to talk about is a concept of a template. The idea of a template is that we provide a model that captures the definitions and the tasks and the operations of a particular application. Today in Visual Sim, our focus has primarily been on discrete building blocks like processors, memories, traffic, stochastic processes, plotters, things like that. We want to move away from that to being able to provide a complete solution in the context of an application. So, for example, I'm going to pick up an application right here which emulates a radar system. So it actually has two things. It does both the pulse Doppler and the scatter radar system. And it goes right from the time that you acquire the signals, the pulses that are coming in. It's sends out electromagnetic wave, gets the pulses back, captures it here, which is on the analog side, goes through a sequence of processing. Like some of these are parallel processing, some of them are just sequential, and end up with either a static, identifier or a movement identifier. So it has two different outputs that comes out. Now, every one of these blocks are being modeled in the details of three different things. The first is what are the inputs and outputs, especially in terms of data sizes. The second is what is the operations that are possible, either based on some mode detection or based on samples or based on the pulse or based on any other attribute, like for example, in this case, the buffer for this one. So it captures all the detail as it flow that will happen in your flow. What this does not capture is it does not capture the signal processing associated with, say, an FFT or a matrix transport. But apart from that, it captures all the performance details. What do you need for the performance details? There are three main things you need for the performance detail. One is the amount of number of cycles, which is the amount of time it takes to execute on a processor. The second thing is where is it being executed? Is it a movement across the PCI from one cluster to another cluster? Or is it an execution of the DSP? But to do the execution of the DSP, it may have a sequence of other things it has to complete. The third thing is what does it break it down into smaller data sizes to do the operations? For example, if I open this block right here and expand this view, you can actually see. So it comes in, it selects which case is it going to do. It's 1, 2, or 3. It goes into one of these. And within these, we select the mode, which is the IDs, and it selects which mode it's going to go. That is going to go there, or it's going to go here. And then here's the third thing, which is in this case, I'm first taking the first 400 bytes and processing it, then taking the second 400 bytes and processing. Now, the processing itself is not done over here. If you notice, there's no delays, there's no buffering, none of those things. Those are all occurring on the hardware system. So we're only describing what is happening through every one of these blocks, either using parameters or using certain computations. So for example, here it takes certain input ideas, and then it goes and gets certain attributes. Like here, the length is the most important one, which is getting from a memory variable right over here. And then it's going ahead and doing the calculation to come up with how many cycles it's going to take for the 64-bit processor. This is the main aspect that we need, because this is the one that's sent over to the hardware to say process for this amount of time with this amount of delay. The samples or the length or the bytes in this particular case, it converts all of them into bytes, is used for, like for example, the movement of data on the PCI or say on the Ethernet or things like that. So this is what a template needs to have. It needs to capture all, see the data comes in, what are all the different modes, which are parameters over here, or they can be dynamic based on the data coming in. Does the computation of the length and the or the data sizes and the cycles, and then it sends it off to the dispatcher and gets it back. And of course, you could be doing it multiple times. In this case, it does it twice, which is the first 400 and then the next 400 bytes. Different modes can do something completely different. Here, for example, it gets the first 400 and then it just wraps up. Or here it does the whole thing. It does a column or row at a time. So you can have different types of processing that can happen in each one of these modules that you see here. So this is what a template is all about. Now, looking at it in more detail, there are a few items that you need to worry about when you're looking at it. Now, remember when I told you the signal processing is not included in it. Eventually, we want to include it, but for now, it's not there. What we're capturing right now is the performance related. Now, you're going to ask the question, what about the power consumption? The power consumption is based in the hardware. So depending on what the execution is going to be, the power is going to change, because it's going to turn on the PCI or shut down one of the cores or any combination of things. Now, if you look at the template, that flow we saw there, the most important thing is the inputs. You can have a large number of inputs, not just one or two, but it can be probably 50, 100 inputs, depending on the particular application. Now, we had one system where the brake system where we had about 8 templates. We have other display system where we had about 30 templates. I'm sorry, 30 inputs. Now, the next thing to look at is the sequence of operations, which is what we saw over here. Which is, this goes into the FPGAs and cache, then FFT, matrix transpose, the processing, then the complex modular processing, buffering, and then target separation. As I said, we're not doing the internal signal processing, just have to understand exactly what is the sequence and what is the different variations in each one of those sequences. That's where the parameters come in. What are the parameters? So for example, going back here, if I look at say the FFT, I do have to convert from fixed to float, how many cycles? To do a complex multiplication, how many cycles? So these are things that are hard-coded into it, but they set as a parameter, which means the user can modify it based on their particular design. So again, we're making this as rigid as possible in the sense that it has a whole flow, but flexible as possible by providing them different parameters to try out different experiments. Now, we want to identify all the information associated with each signal in each operation. Now, we have a concept called data structure. Now, a data structure in Visual Sim corresponds to the signal or the transaction that is flowing through So when I see this from here to here to here, there's a what's called a struct or a data structure that flows through all of them. Now, the data structure doesn't necessarily have to correlate with what really happens in implementation. So what that means is I can have more information in the data structure than I may have in my real system. So if I look at this data structure for this radar, I notice there's quite a few of them. So some of these are, to identify whether it's a CPI or a PRI signal. Others are lengths and samples. Identify is it I sample or a Q sample? Is it I or Q channel? Is it static or motion? And then there's a whole bunch which ID it is. Which one? What is the task dispatch numbers? There's a whole lot of variety of items that are stored here. Now, these are all related to the signal. This one here, for example, is related to our computation. These two items here are what's sent over to the hardware for either a delay on a bus or a delay based on processing cycles. And then, of course, these things here are telling you which device I'm actually going to be sending it to. So the data structure can have a variety of information in them. Now, we've already talked about this. I'm just going to reiterate: decision at each operation point. So this was the number of nodes, the types of data, the size of samples. So now this is specific for radar. Now, when you start looking at autonomous driving or other components, the behavior may be completely different. So you may have other types of IDs that you want to associate with it. So for example, if we take autonomous driving, the data coming in may come from a camera, a radar, a LiDAR, or some other interface. So based on what comes in, the operation might be slightly different. Then, of course, we talk about the connection, how they're all connected, the data sizes. Then we talk about the cycle computation and how is the data processed at each node. Remember, we showed you where the first 400 and then the second 400 was the top one. So like that, is it different for different data inputs? Is it different for different modes? Well, how is it, or why is it different? And then we need to capture all those differences. Now comes the interesting part, which is, remember, we have all these different blocks, and depending on functions and modes, we could map them to different hardware systems. Right? So we need some sort of a table to emulate that. Now, this model here has a pretty complex table. So we've got all of these different entities up here, the function ID, task ID, all of these different elements. And based on each one of them, maybe sending it to a PCI or the first module DSP, or it doesn't do anything, or it goes to other elements. So there's a variety of things for each of the combination of things that we have here. Like for example, some of these say that DSP link, so it's really on the the transfer, while the core means the executing on the processor. EP is one of the other processing flows, so it's going to like the memories and things like that. And of course, here's where we provide all this information. And finally, how do we implement the whole flow? Now, one of the things that's critical is that we're going to see this in a few of our more detailed models, is that the items can be delayed in the flow. Like for example, if I take an analog front end, right now we don't do anything in analog, so we don't need to worry about mapping to hardware. So we just say, here's an analog front end, we're done with it. Okay? Or there could be another item like an FPGA where we're using it only as a cache. We don't need to have it move back and forth. We can just say, okay, here's an FPGA module, it's a cache, the size of the buffer is so much. So if you look back into our model over here, the buffer here is a parameter, which is a top level parameter. So we just say, what is the buffer threshold? That's all we need. So we're not doing anything else. The entire buffer has been implemented on FPGA and it's listed right over here. And then, of course, the rest we'll have to use some dispatcher to map them to the hardware platform. So this is a detailed view on how we create these templates. Now let's break it down into something simpler and smaller to create a behavior. So we're going to take something that's a little generic, okay? So we've got a simple hardware system. It's got two cores, it's got an I/O, a DSP, and it's got two buses and a bridge between them. So we assume that this is your application. So you have some sensor data or some trigger or an interrupt that triggers this, and it goes through the sequence. Now, there's a rate here that determines, how much, how often these triggers are coming in. And of course, associated with each one of these tasks, there's some sort of a cycle count, or how much is the delay associated with each one of them. The third aspect is the mapping. So we get to map this. Each one of these tasks could be mapped to one or the other. So here you notice task 1 goes to I/O, task 2 to CPU, task 2 DSP, and task 4 to the I/O again. Now, what we don't capture here, which is something that has to be captured separately, is the movement. So from I/O to CPU or CPU to DSP, notice here we go bridge 1, bus 1, bridge, bus 2, DSP. While from DSP to I/O, it's the other way around, to bridge 2, bus 2, bridge, bus 1, I/O. So in addition to capturing the sequence of tasks, we're also capturing the flows here, okay, which is the transfers. Now, why is this important? A lot of times when we're capturing the latency, we will find out that these individual units don't consume a lot of time. Most of the time is related to transfer. Why? Because these end up being extremely fast, utilization is very low, and most of the utilization are here. And that is what we'll find in most of the designs. Most designs, the buses, the memory access, that is where the bottleneck is, not in the processing core or the accelerators. Now, of course, there are times when you want to move things to an accelerator, and the reason we do that is because it's just more convenient or more appropriate to put them in an accelerator, because they'll be just churning a lot of CPU cycles, which consumes more power. It just locks out a whole lot of tasks. Even though the utilization may not be high, it just locks out during a period of time. So that's one of the reasons why we use accelerators a lot. Okay? Now, one of the things that's interesting, if you notice with that radar system and everything here, is at any time, depending on what the rate is, there could be one task being executed here in each one of these to be executing, and also there could be data movement between them happening at the same time. So if you look at it, there's a lot of different activities happening just with this one flow. Now, it all depends on this one. Now, obviously, if I'm going to have these also do a lot of processing where multiple of them are coming in, it means that you're going to have buffers in each one of these that have to be maintained, which is the second area of concern in most designs, which is what should be the buffer sizing at each one of these. Okay? Apart from the hardware and memory, the buffer sizing becomes the second big element here. Now, one of the things we may find in certain applications, like for example, in the radar system, we didn't see it because it's just one single flow. But when you come to autonomous driving, there could be, turning on a turn signal while at the same time having the steering wheel make the turn. Those two actions happen. And many of them may be using the same sensor data, may be using the same interrupt trigger, and also using the similar set of hardware or ECU components. So let's add another one here. And you can see the mapping is slightly different, obviously, which means the transfers are also slightly different. So what are we seeing over here? What we're seeing over here now is I got one trigger over here that's triggering these, another trigger over here that's triggering these. Now, the interesting thing is all of these should be busy at any time, and the transfers between them can also be busy at any time, similarly for these. So these are the types of templates that we want to build up. So this is part one. We build up the templates and we provide them a mechanism to map it to these hardware components. Now, two things can happen. One is the templates can change, which means they may add a few more elements to the base template. or the transfers might change, which means, like rather than go across the bridge, I might put all the processors on the same bus. So the transfers also can change. So we need to have the flexibility to provide that capability in these templates for building. Okay. Now, what are the types of analysis? There's a lot of analysis you can do. So we need to be intelligent on what are the analysis we want to provide. Now, in this particular case, we're looking at the response time. So what we did was we had two tasks. They have their own independent trigger rate. They have their own sequence with their own mapping and their own transfers. Now, what we did was rather than modifying the application, which can be done, we're modifying only the clock speed of the hardware. So we tried two of these, 200 and 400, and we get different methods. In this case, it's a very specific case. I'll talk about this, but I'm going to go into the model and go into more details there. So, for example, over here, you can see that 200 is the red, 200 megahertz is red, and 400 megahertz is the blue. What are we looking at here? We're looking at the time it takes for task 2 from the time it's triggered to the time it completed. So that's these points here. Every dot corresponds to every trigger or interrupt coming in to the time it actually takes to complete. So blue dots, as you can see, they're obviously much less than the time taken than compared to the red dot. The primary reason being is that the blue dots are running on a much faster bus. But what we want to really capture is these critical points here. Notice at these points, the blue dots are actually taking much longer than the red dots. Why is that significant? I just increased the speed of my system and I'm not getting performance for many applications. I'm actually finding it's much slower. So this is something that has to be understood by the hardware guy. For example, you go buy a MacBook Air and you find when I have 3 applications running, it actually slows down my system. Whereas on a Windows machine, I can do 10 applications and there's no problem. So what's going to happen? The MacBook Air is not going to be looked with the same feel as the Windows machine. And if you want to charge a premium or you want to charge, say, like a differentiated value, you have to determine why you're having these bottlenecks and then resolve them. So now I'm going to go back into the model. We can look at the model in detail. So here's the thing that we're looking at in the model. We have, as you can see, the hardware, and you can see this is the 2 tasks. And you can see over here, we have the, as we saw here, the task 1, task 2, task 3, task 4. This is the second one, 1, 2, 3, and 4. And then we define the transfers over here. This was 1, 2, 3, and here was 1, 2. So we got these 3 transfers on both of them. Okay. Now these were the interrupts of these sensors and the triggering them. So we described these. Now, as far as these templates goes, what are we trying to do? We're trying to create these as something that is specific to each application. Here it's generic, but we need to replace this with the other applications where we'll be generating these templates. Okay, and this is what is the first project that I'm having you guys do for this template generation. But I still want to go through the process of explaining. Now, once you define these templates, what you do is, you go to Google searches, you look at like documents, you look at exactly what happens. Then look for like MATLAB models of your signal processing or control flow models to try to understand what is happening within each of these blocks. Or you can even look at data sheets of like products that are in the market, so you can understand where you can get information about these flows and what happens inside each one. So once you've described all of these, then what you want to do is you want to map them. So what I'm going to do now is I'm going to look at each one of these blocks so you understand how they create. The first is the traffic. Here the main thing is the sensor rate. Here we're describing details about the signal that came in. So you got a set of these parameters or set of these fields that we're adding to this particular sensor data. Now let's go look into one of these. Now here's the thing that's important. If you go into one of these, what are we seeing? We're seeing 3 blocks. So what are these 3 blocks doing? The first one is specifying a timestamp as to when it was created. The second one, if you remember, we talked about the delay. So here the delays are actually being defined separately outside of the flow. So we're just saying that we're going to map it somewhere, but we're not specifying the delay here. The reason for doing that is because if I'm going to be doing it on CPU 1 versus CPU 2, my delay is going to be completely different. So at that point, I want to change it, not do it inside and hard code it in the block. So that's why these parameters have to be, referenced up so we can go and get it from somewhere else. Now, we can be doing a variety of other things. For example, here we're doing some tracking. We may not need some of these, but just so that we can get statistics to capture exactly what is happening. Now, if you notice, this was just the I/O, which means you're just going and processing it here and coming back. This one here is a little more complicated. Remember, we go from I/O to CPU was just I/O bus 1 CPU, but then CPU 1 to DSP was bus 1 bridge bus 2. So that becomes a parameter of the block. In this case, you just see it's bus 1, but here you'll see it's bus 1 bridge bus 2. So again, you have to set it up in the template so user can enter those easily. So it comes in here, same thing with setting up the timestamps. Then what we do is we go through the loop, we get the first one, we find out what is the first element, and then we use that one. So here, if I look at this, I'm getting the 0 from this particular field, which is that bus 1 bridge bus 2. I'm getting the first element, and then I'm removing that from the list, and that becomes my element over here to say this is where I want to map it to. So I want to map it to the bridge, or I want to map it to something else. Okay, and so it does that, and then here it checks to see if there are more elements. If there are more elements, then it continues through the loop. If there are no more elements, it just drops it and sends it off here. So this is where we check to see if the length is greater than 0 or the length is 0. With 0, it says, hey, I'm done, go to the next step. If not, I'm going through a loop. So if you notice in the earlier one, we didn't have the radar, we didn't have a loop. We just went 400 bytes came out. Here, we're going through multiple things and we're going through loops here. So depending on your thing, you might do one or the other. And then when they're done, similar to what we saw in that radar system, we generate statistics. So again, we have to research to find out what are the statistics that are relevant. In this case, the relevant one was the latency and a histogram associated with the latency. Those were two that we were interested in. So this is on the template or the behavior side. Architecture side, in this case, what we have is quite simple. What we do, this is a starting model. So we just have like a system resource to emulate each one of these blocks. This is a system resource for each one of them. They're all identical. Now, associated with each one, we have a name and a speed. That's only two we're interested right now. Now, some of these other models may get a lot more complicated, but these will start with just this. Now, here you notice the application 1, application 2. It says these are the 4 sequence of tasks. Remember, we have those tasks as bubbles. These are the 4 for application 1. These are the 4 for application 2. And this was the delay in each one of them. So we're mapping each one here. So for example, over here, taking app 1 execution, and then that's the app 1 time. So we're taking each one of these and putting it in one of these items here. Now, in this case, what we're also doing, which I think is very critical and we should make it a standard practice, is add in the power table. So in the power table, we provide information on all the modules, CPU 1, 2, DSP bus 1, bus 2, bridge is kind of missing here, that's a good point. We need to have that. And then we have the power. I noticed here, the power is linked to the speed of the respective devices. So if I get the speed to, say, 75 megahertz, the power will be one value. While if it becomes 200 megahertz, the power will be a different value. Here, for example, we're assuming it to be very linear, may not be maybe exponential, but for now, we'll assume them to be linear. If it's exponential, we'll try out some other formula for that. Okay? But the main idea here to capture is the behavior, including the sources, and these could be multiple. You might have to wait on multiple data to arrive. Sources, what are the tasks, the transfers between the tasks. So you have these here. Then how the mapping happens to each one. So you build this up, and then you build your power tables. So this is, in a sense, how you describe a particular system or your application. So this, if I can do this, say for like say an autonomous driving, or I do this for like say a networking application or an IoT, the user immediately knows, hey, I realize this, I associate with this, boom, it'll be very easy for me to go ahead and create this application or extend just this application to very quickly define what they're building. So that way the time taken for a user to ramp up reduces substantially. Okay, at this point I'm going to take a quick break. I'm going to let anybody ask any questions before I go on to the next model. Any questions on any of these?
So I have one question. How do you debug that model?
Very good question. So one of the things that we want to consider is the debugging of these models as well. So we should provide, oops, close. That's a very good question. We should consider debugging as an important and standard functionality of what it is that we're doing. So how do we debug the model? There are three things we want to use to debug the model. First and foremost is, are we getting any outputs here? If we're getting any outputs, that's a good thing. The second thing is we have these two parameters called, and I'm going to go ahead and run the model so I can show you on the output. Oops, we did not capture that. So let me capture, I'm going to do a listen report here. But capture the data structure that terminates. Okay. So when we have these data structures, one thing you'll notice is that we have this thing called a trace array and a time array. And that's telling you what is the sequence it's going. So in this case, it's our it's T1, which is the first task, so first application. So you can say we went through IO, which is correct. Then we went bus, then we went CPU, then we went bus, bridge, bus. Then we did the DSP. Then we did the bus, bridge, bus again. And then we came to IO. So this tells me two things. One is the sequence was all correct. And and the second thing is that the sequence completed. Those are two things that are critical. The next thing we want to look at is we want to look at where was the delay the most. So we want to find out if there is any bottleneck. And that's where we start adding other pieces of information into the system here. Here. So we can start generating other types, and this is where we have to come up with what are the interesting things that we want to do. So for example, here we say this was the processing time inputs, and this was the queuing times. That's sorry, the processing cycles, and this was processing plus queuing delays. Okay, and these were the associated transfer times, and this was the total time. So what are we seeing here? We know now that if these two don't match, that is, this multiplied by the clock speed, if they don't match this and they're above certain threshold or limits, then we know that there's too much of bottleneck somewhere in the system. The second thing we want to look at is we want to compare the transfer time versus the execution time. If this is too high, that's also an issue that we need to consider. So these become the standard way of debugging your system. Now, the first one I showed you, the arrays, those are already standard generated by these blocks. The user doesn't have to do anything. But then these other things we're looking at, like the looking at that comparison between the CPU time versus the transfer time, things like that. Those we have to use our new diagnostic block that we're building up, and some of these functionalities already available in that. So you can look at the output and see if the results are correct. Those are a couple of ways that you can incorporate it. Daryl, do you want to add anything else to it?
I would say that sometimes you can send messages that certain tasks, subtasks have completed.
That's a very good point. So you could, if you want to do it in between, you can send messages out from the blocks. So you can say that at this point it completed, and you can send a message to another block. Why is that important? Moini's diagnostic block actually has some of that, where I might have multiple flows, and they may actually at some point even interject, which means I might need data from flow 1 and I may need data from flow 2. So I want to figure out if the previous tasks were completing, or is it just that this one task requires a flow from 2 others coming in, suddenly stops operating, right? So the thing is, if these messages are sent out, that I know, okay, task 1 completed, task 2 did not complete. So the bottleneck is in task 2. I need to look at task 2 more. So that's a very good point. You may want to use it to send messages. But for now, the template is not going to do any of those things, because we want to have it as a completely well-defined, and you want to be able to extract data to the diagnostic block and be able to capture the all of those messages as Daryl was mentioned. Any others, Daryl?
Yeah, there's one other factor, and that is when you go to these resources, they may have an implicit width of bytes or bits or whatever, how you measure it. And that could, so the problem with the template is that it's like a cookie cutter. And a lot of designs don't fit into a cookie cutter. And so I think having the width to the resource as like a parameter or an ability to change that. Now, obviously, I can change the speed, but if the customer sees that you double the speed and really you're just because you're trying to model it with double the width, it's probably better to put double the width to that processor.
That's a very, very good point. If you remember going back to this radar system, you notice that here we were not just computing the sorry, wrong block. If you go back here, we were computing both the T bytes and we were computing the T ciphers. It's very important, and this is a very important consideration, because the reason we were doing it is, if I was going into the PCI bus there, and I have, say, let me go up to the top level first. Notice here, I've got the width and I've got the bus width in bytes here. So in this case, the delay is based not just on the size of the data, but it's also based on the on the length of the data coming in divided by the width, and also you may add additional items like a turnaround cycle. Again, that's on the hardware side, would not be on the template side. The template would just send in information about the data size and the cycle count. But that's a very good point to consider as well when you're building up your templates. Any others?
You might mention that we have the array plotter. So when you get into these complex systems, you have a lot of things going on. And the array plotter has the ability to plot, you just fill up an array with some values and you can see kind of what the system is doing. So the biggest problem with these larger systems, and that's, the trend, is that you can't see what's going on. You may have all of these parameters, you may have all of the values, you can only see some output coming out of it. But it would be really nice to see how, sort of like a utilization of each, let's say, processor or resource, and you could see it in one plot. Now you do have a histogram there of the processing. That's kind of going in that direction.
Good point, Moini. This applies to what you're doing, which is, for example, over here, right, when you generate this sequence over here, right, what Daryl's talking about is an easier way to view these. See, you have your throughput, you have your time, and you have your trace. Is there an easier way to view this data? I mean, the array plotting is one way. Are there other ways to look at it? But that is something you should consider as part of the diagnostic plot as well, Moini.
Hello?
Yeah.
Yeah, we had the trace plotter, right? We built it for the Denso.
Yes, so that could be another one that we could also utilize. Absolutely. So that, I think that could be another one that we should try to productize also. I think it's a good point. Daryl, if I continue on to the next one.
Yeah, go ahead.
So this one was a very generic template, but it did show you very well how you can take multiple application templates, create templates, create interrupts, and then map them to hardware platforms. So this is the basic of any system you're going to be building, and it also helps you understand how you can create very complex architectures and do complex research and analysis. Okay? Now, we're moving on to the next one, which is an application. So this is a real application. And what we have is a large number of these IoT devices. And don't get locked out by IoT thinking it's a watch or a phone or something. It can be a whole variety of things. It can be sensors in an industrial plant where we're trying to figure out if the bearings are wearing out that they reach 20%, or they can be elements in your car that are providing vitals about the car, like the amount of fuel, the water temperature, other aspects to a central data center. Could be any one of these things. So, but most of them have a very similar approach, and that's where the IoT template works. And then I'm going to walk you through that. What you have over here is 4 basic elements. So you have the analog front end, you have a processor, you have your modems, and the radio transceivers. Of course, you can incorporate the antenna as well, but I'm just including that in the radio transceiver. Now, one of the things with the radar or with that hardware system or the electronics you saw was that it was all self-contained. It was a block within itself. It wasn't, we were not going outside of the block. But now with these IoTs, it's insufficient to just model the IoT. You have to take into consideration other aspects of the system, primarily the network, because all IoTs have some communication to a data center and come back. Now, it can be that these IoTs go only to a local hub, like for example, an industrial plant. You may have all these 20,000 IoTs in the plant that communicate to a data center wirelessly that is within the data center. So it's not, within that industrial plant, it's not going outside. So it sends it out to the data center. From that point onwards, it will be local processing to decide, should I keep it here or send it to a centralized, which is in the cloud? So this would not be a cloud, to be inside that center versus going on the internet to getting to a cloud. There's 2 aspects. Why is that important? There's 2 reasons. One is security, which is here it's public, here it's private. So I might much rather keep everything private and not send it to the data center. The other aspect is latency. I can do some of the work here and get response back immediately, or I can do it here, get response back, or I can do it here and get response back. These could be in nanoseconds, these could be in microseconds, these could be in milliseconds. So depending on the criticality and the time bound or time deadline, I might do it in one of these 3 locations. Now, what do we have to consider here? The considerations can be the power consumed, because if I'm doing all the processing here, the RISC-V is going to do all the processing overhead. While if I send it out here a lot, then these guys are going to consume a lot of power. Now, which one's better, which one's worse, really depends on how much battery capacity you have, what is the time criticality, as I mentioned. So it's those aspects that have to be considered in putting these things together. Now, these are the basic blocks. Now, there's things that happen between these basic blocks. So in IoT, there's really three major things happening. The first is some data acquisition, which is certain sensors. Like you take your watch. What is the main thing your watch is acquiring? It's acquiring your pulse, right? And another one is it's acquiring some oxygen information. Those are two basic things it's acquiring from your hand. So each of those is considered an analog front. It's considered a sensor that is fed into an analog front end. Remember, those are the vitals are in analog; they're not digital. Your body doesn't work in digital; works in analog. So from there, the front end converts it into a digital that the processor core understands. In this case, RISC-V, but it can be ARM or it can be any other processor as well. That's the first aspect, which is conversion. So it's acquisition, conversion. Second aspect is some sort of processing that happens in code, a sequence of things that happen. Okay? Now remember, these IoTs are pretty small, so they typically may just have a few processor cores, a bus, a memory, a flash, and maybe a few other elements like the analog front-end input, maybe a DMA. That's what they'll be. So they'll be very small in what they can do. And then, of course, once they're done, you have the state machine associated with your modem or your interface to the network. So those are the 3 or 4 aspects that you have in your system. Now, as you start moving to 5G and things like that, there are some more things that we have to consider. Over here, the baseband is no longer just a simple single type of modulation process. Depending on the data, depending on the use case, depending on the channel, depending on the distance, the power, signal power, all of those, I could be doing a different type of a modulation scheme. Like I could go anything from a QPSK all the way to a 256 quarter amplitude modulation or QAM. That is one aspect. The second thing is the antenna. What type of an antenna I'm going to use is going to impact my power. It's also going to impact, what is my throughput to get to the network hub. And of course, the third thing is what's going to be my data sizes, and then associated that is what is the channel. Because some of it can be inside of the building, part of it can be outside of the building, which is like more like like humidity or like dust particles or things like that, or rain aspects such as those that might go across. So it's there could be multiple channel models that you go across before you get to the network hub. Okay? So this is a critical one that you should look at building, because IoTs are things that are like everyday application that everybody wants to build. Now, let's look at this IoT and how it was built. Now, this template, in my opinion, is lacking a few things, so somebody can take this and start building it up. Let's explain here. I've got one sensor, multiple one sensor. The AFE here is a simple delay. We've got other models that have more detailed AFE information, which is analog front end. We may want to incorporate that in, and the ability for the user to add multiple sensors. That's one thing we need to do. 2 things we need to do. Add more ability to add more sensors, expand the AFE to bring in a more accurate version. The MCU. Now this one here is not very detailed. We may want to add some more logic, but also make it into a separate entity, because we want to create 2 or 3 variations. Typically, they use M3 from ARM, or they use a RISC-V core. So we want to create 2 or 3 of these variations that the user can drag and drop. And of course, associated with this, which is missing here, which is got a sequence of instructions. What is missing here is what is the sequence of application that we saw the tasks in the previous one. So while we do this, we should also have something here which describes more of the tasks, and then move the MCU over here so that the flow can be described as well. So in this case, we were just saying that whatever data comes in, we are processing it and sending it out. We're not breaking down the processing into detailed components, which is something that we should consider having to see what the most common functions that are done in these IoTs and then incorporate them. You may find that there are multiple of these flows, not just one flow. So we've got to do our research to figure out, well, maybe it's an application. So if I'm doing an automotive flow versus I'm doing industrial flow versus the aircraft flow, things that we might have multiple task flows, and then the the hardware platform itself could be here. Those could also be multiple of those as well that you could have. Now, this one here, the Bluetooth core, the low energy Bluetooth over here, is being modeled with the state machine. So that is something we can also incorporate the start, including for each one of those modems, we can have the state machine to describe what is the communication with the channel. So, do I like turn it off, turn it on, or do I, keep it on for an extended period of time? Or, when do I accept things? Do I accept data at regular intervals, or do I always keep accepting? What are the kinds of things? And many of these cases, these would be standard state machines that are available in the data sheet or in the spec, in this case, the low energy spec, and we will just incorporate that state machine. I'm going to walk through each one of these in the blocks that you're going to see. And of course, in this case, the radio transceiver is fairly simple, just a delay to send it out, but this is where you have to add the analog, the antenna, and also connect it to a channel. I'll show you some of those as well, but for now, we'll just walk you through this block diagram. Now, associated with this MCU and with the Bluetooth, we have a power table which maintains all the information. Plus, in this case, for all the activity, we have a battery block as well. So we're mapping it to a battery block, and we also have an energy harvester. Energy harvesters are where you're continuously getting charged based on certain, certain activity. It could be that you're plugged into a wall socket, or you have a piezoelectric, which is some movements, like charging your system, or you have a solar panel. I mean, any of those kind of things that you have as your energy harvester. So what that means is that while this thing is discharging it, this thing is charging. So you have charging and discharging happening in parallel to look at. So all of that is modeled over here. And then, of course, we talked about the channel. It goes into a network over here, and then it goes across multiple routers, and it goes to the data center, and then it comes back with your responses. So we have the flow, we have the hardware, we have the battery system, we have the local hubs, internet, all the way to the data center. So with the IoT, this is actually something that's very important. With the IoT, we're modeling right from the interface of the sensor to the data center and back. This is a critical functionality because there isn't really any other way to do this. And we want to be able to create a lot of these different applications here and possibly add a lot more of these modems here so that we can start, highlighting our capabilities in all the upcoming areas. Obviously, we don't want to go backwards, we want to go forwards. We want to look at what are the new areas that are coming up. So that's a critical aspect of it. Right? Now, of course, the other things here is we may want to add other things like the baseband, more details on the antenna, things like that also. So when I go into the system, I'm going to go in here. So this is an existing model in the tool. So now here's the thing. This one is my energy harvester. This is taken out of the power library. Right here. This is a battery again taken out of the power library, the power table taken out of the thing. So all of these are from the power library. And now here, the sensor is of course a traffic generator, and we have certain attributes which are parameters at top level here. Now realize that I could have multiple of these. Now in this particular case, this thing here, as I mentioned, is just the based on the size of the data, it's just randomly generating a latency. Now, This is where the first thing, the change has to happen, because if I take a real system, so you could have multiple of these, and then here there could be a lot more complex processing. I'm not going to go into details here, but this is what could be happening in the, this is a particular device called the AD9361. It's a transceiver from Analog Devices. As you can see, for the different INQs with 2 different channels and your analog interfaces, for each one of them, install those here. Each one of them, there's a sequence of operations that occurs. Now, each one of these, if I go into it, just has a way to compute the clock rate. You see what it is? You can see what your delay is. So it computes the clock rate, computes the delay. And that's how it delays it and sends it out. And you can see here the first digital filter, the transmitter signal path is the programmable polyphase FIR filter. Go to the next one. The fixed coefficient half bandwidth interpolating. Now notice, this is what is being done, but we're not actually implementing that signal processing algorithm. We're just taking the delay value associated by calculating here the sample rate. That's a multiplication factor. Again, both this is from the data sheet. We calculate the number of taps at the end of the data sheet or from the user's input for this particular block. And then we calculate what the delay is. And that's how we're doing it for each one of these building blocks over here, and then a mux to bring the INQ together and send them out. Now, obviously, for the analog, the flow is slightly different. When I look at this, see, this is a single pole low pass filter. And that's the sequence of things you have over there. So this is for the analog interfaces, they're slightly different. So what you saw earlier on the sensor, which is a simple delay, we have to take that and add this logic over there. So we need to add something that's a lot more complicated. Now, once it's completed that, then we have to add the signal processing element to these flows here, which is, you can see here, we're doing the LDPCs, the encoding, interleaving. So we got to find out what are the things that happen on these elements as well. So we have to calculate that aspect also. So you can see what is the sequence of functions that are happening, and then you're doing your computation right over here. So again, now it's no longer just just a delay function, but we're actually going through a sequence of all these activities. So if I go look at the interleaver, and I get the depth, and I get the out bytes, and I do my computation. So it's what you're seeing now is we're seeing an actual system where we're adding more and more of these kind of logical, more and more of these functional details in the system to make it very, very detailed. So again, the user could put in just a delay, or he would replace it with that analog front end, and have a more detailed model of the system. And of course, in this case, the hardware here, and most hardware is going to look very similar to this. So you have a processor, you have a DMA, you have some sort of a device interface that is from an analog or from a from a sensor coming in, and then you have some memory. Maybe you might have 2 or 3 other memories also. But that's in essence what most of the hardware is going to look like. And we can look at a few of them and just create a standard template that we could incorporate for that functionality also. Okay. So this is, we define the define the power, we define the interface, the analog front end, we added the MCU, and now we look at the Bluetooth. So the Bluetooth, we have the Bluetooth, in this case we have the encryption. Again, the encryption here is a delay, depending on it's a 16 bytes, and then it's 1 megahertz. So that's the encryption delay. But you could potentially add more logic to that as well, based on other attributes, or you could potentially even add the encryption algorithm right here. It's a delay for the encryption. Now, the link layer here. So this one over here, when it comes into the wake up, it sends it out to wake up the Bluetooth module over here. So Bluetooth now is the finite state machine. So this is part of the standard that you would see on a low energy Bluetooth. So you can see the different states. Notice here there's not a whole lot of states here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 states. That's what you really have here. Now 9 states. But you could have lesser or more number of states depending on your particular application. But now the state machine is actually quite interesting. The reason is the you can control the state machine based on your input trigger. Because notice these guard masks, they're based on what's coming in, and you can also control it based on just the standard delay function. So that is another possibility as well. And of course, so the state machine allows you to describe in detail the communication with your network hub. So notice now, we have added all the items to the flow. So we've got every single element in the flow that we have for an IoT device, including all the encryption, your Bluetooth interface or any other interface. You can also look at the link layer hardware, which is the L2 layer. So you got the wireless, and then you got the Bluetooth right here, communications. So notice here we don't add much to the baseband. Again, that's some logic that we can add. This one here is more detailed because this is the Bluetooth interface itself. So this is doing all the logic related to the Bluetooth as well. Okay. Now that you've seen this complete flow over here, remember this is what we want to start building up for other systems. Now we want to look at how many sensors that are typically there in these applications. What are the clock speeds of the sensors? What is the data size of these sensors? What are the different attributes that these sensors have, and start enhancing these modules for adding that functionality as well. So we come up with a few of these different IoT modules, and we add this functionality, and then we would have a template that's available for any IoT application. In this case, the network is fairly simple, and we like to keep it like this for most IoT systems. It just sends it out to a network node block, and the network node block goes across using a routing table, which is right over here. Routing table sends it off onto the network, and in this case, the data center is simple, but again, you might need to add a more complicated. In this case, just comes in with a delay and sends it back. But we might want to add a more interesting data center model as well, where it comes in on any one of these 20 different communication channels. It would, depending on the data, or just randomly send it to one of the processing units, and each one of those, depending on the data size, may go virtually to some set of storage devices. Typically, how a data center would operate. So, building a data center model would also be something that we could, do with this particular design. So, what are the typical types of analysis that people do with these kind of systems? Obviously, within IoT, as I mentioned, the power would be critical. The second thing is, from the time that the sensor starts generating data, what is the time that it gets response time? I would say these two are the main. The third one, the side benefit, is how much of efficiency am I getting on the processing? The reason that's important is most IoTs are cost sensitive. So rather than going with an expensive $3 or $4 MCU, I'm going to go with a $1 if I don't need so much processing. So that's a very important aspect. The other aspect is on looking at the analog front end, looking at the Bluetooth, all of those things. Other ways I can reduce cost. Maybe I don't need a very powerful Bluetooth, or I can get away with a less frequency analog an AFE or like the ATD converters, so I can save costs there. So there are those kind of things to be looking at the efficiency of the system. The other aspect is regarding the power is looking at optimizing the attributes related to optimize, say, my modem, in this case, the Bluetooth, which shows me, like, notice most of the time it's transmission and there's very little receiving. So in this case, like, I don't need to keep advertising a lot. I could reduce the amount of advertising time. Only advertise as and when it is required. So there are those kind of things to consider. So depending on what it is that you want to do, you may want to look at different aspects. For example, here I can see it's highly unoptimized because what I'm seeing is over the entire period of time, even though the processing is only at these points, the entire period of time, the power is kept at a high level. So if there are ways that we can do power management to reduce the power, that would be something that would make it very powerful. Of course, you can see what the average power is on each of the devices and what is the response time to go from the device to the network and come back, including all the hardware and other aspects as well. So if you can look at this now, you're looking at how do I save cost, how do I make the network more efficient, how do I take care of the power consumption within each one of the systems. So this is, you can look at it as an IoT, or you can look at it as a 5G application, or you can look at it as a Wi-Fi system, or you can look at any aspect, but you're really optimizing from the sensor interfaces to the data center and back. It's a pretty complicated kind of design here. So this was the second one I wanted to show you. Any questions on this? Hopefully I'm not losing people. Is everybody right away?
So when we said making the template, do we have to go into details such as implementing the state machine and such? Oh.
Good question. So what I think we should do is I think we should have two variations. One of them, if you notice, the AFE in this particular model was a simple delay. So we can have that variation, and then of course you can have the more detailed one which you saw with the signal processing. So my recommendation is we have both of those. So depending on what level of detail the user is at, we could provide, they could select one or the other.
Okay.
But I would definitely start with the more abstract one and then put in the details, the more detailed one later.
Okay.
Any other questions? Okay. So there's another one that I want to show you. This is a little different from some of the designs that you might have seen, in the sense that this one here does not show very well as a nice flow diagram, nice block diagram, doesn't show any of those. But it is actually very, very powerful in someone that's coming from an analytical model. Analytical model is an Excel file. So what do I do in an Excel file? I say, each one of these is generating data. It's 10 milliseconds in each one of these nodes, and then it's 5 milliseconds for transfer. I add them all up, and I get a delay. This one takes that and makes it a little more dynamic, which means that if there are say things operating in parallel, one of them can work, the other one cannot work. So one of them will wait while the other one is processing. So the queuing delays there. The other aspect is, for example, on the power, if say nothing's happening, I can shut it off to a much lower state if nothing's happening for a period of time. Those things cannot be captured in an Excel spreadsheet. So that is where we use this kind of a model. Now, obviously, this is something that we need to make generic. Right now, it's a very specific for a CAN bus based automotive system. But we want to look at making this very generic, which means that it can be applied to any application as well that's got distributed processing. So what are we seeing over here? The main thing is that we have independent, think of them as independent computers call them ECUs in a car, or it can be like a high performance system that is it's got like an open VPX or a PCI Express backbone. They have a lot of computer boards connected together between all of them. So why is it important? The reason is some of the sensors and some of the processing may happen locally on each one of these computers, but the main decision thing may happen on a completely different computer board. So all the local processing is done, sent to that, and then I get responses back. Now, when I go across that, I might go, within my same board, say about 4 processors or 4 cores in a processor. I might just do it locally with a shared memory. If it's within the process shared memory, if it's going across process, maybe through a PCIe or a circuit switches. I'm sorry, a cross-bus switch goes across to these other processor memories. Could be that way, or I might have to go across an Ethernet interface, an Ethernet wire, and go to some other box that has the processing on the next system. Where is this used? A lot of supercomputers, flight avionics and aircrafts and things like that. Of course, automotive processing. They all have this kind of very distributed processing that happens. What are the things that you need to worry about? Obviously, the communication between all of these, which is, how do I have a routing table that moves data from, say, one board to another board? Second thing is capacity planning. Capacity planning is on every aspect of the system. How many cores do I need on a processor? How many processors do I need on a board? How much of memory do I need for each processor? What should be the backplane capacity, which is, should it be high speed, low speed? How many channels, all these kind of questions. And of course comes the main part, which is how do I distribute my processing across the system? Which is, do I do all my sensor processing locally and only do the sensor fusion at the central system, or I don't even do single sensor processing locally? I do everything at the, at like a big hub. What is the resource allocation do I handle? Now, let's take this task graph. And this is a standard task graph that we have built for many, many models, but we have to figure out how to productize this and make it a general task graph. So we have task 1 that is sent to task 2, sent to task 3 and 4 for task 2, and there's messages between each one of these. So what are the things that can happen? Obviously, you have these 4 tasks that can be mapped to different processors or cores or different boards themselves. The messages themselves are communication that may be within the same processor to go across boards, or maybe across a backbone to go to another processor, or maybe across an Ethernet interface to go to the network to another box itself. So you have the tasks, you have the messages, so you have the communication between them. Now, this is a model that's specific to the CAN bus. You can put any other bus of choice. So what you see over here, very similar to the very first one we looked at. Remember, we had the I/O and CPU on the first bus, and then you had the bridge and the second bus, and then a DSP and the CPU2. Very similar idea. You have 2 ECUs on CAN 1. You have a bridge, 2 CANs, another bridge, 2 bridges to another CAN. So you have a path that can go from here like this to here, or it can come down to here to here. And you have the 3 ECUs. So messages say I want to go from, say, T1, which is located here, to T3, which is located over here. Once I'm done, I've got to go down this path, come up here, and come over here. Okay. Now, if it is internal, source and destination are the same. If not, they're different. We have to go across. Okay. Oops. So now let me go over to the model. Okay, here we go. So if you notice, this model is not very interesting, meaning that we're not actually putting in a lot of the look and feel and things like that. But associated with every one of these, the ECUs, we got 3 ECUs, ECU 1, 2, and 3. We got the CANs, the CAN 1, 2, 3, and 4. And so we're actually ignoring the bridges in this particular case, which is fine, but we would have to add that also. And of course, we have a dispatcher in the middle, which is the mapper that sends it to one of these. Now, what do we have? We have a signal database. So each one of these signals has a name, has a value. The period is saying how often we're sending it out. The worst case execution time tells me what is the delay for me to get whatever processing I need to get done on that signal and complete it. Does it complete within this time? Now, notice here, these signals are put into M1 and M2. They're all put into M1 and M2 for some reason. And these are later plotting, we can ignore that, so we just focus on these. So each one of these signals gets put into M1 and M2. So those are the destinations. Okay. Now, the messages, these are M1, we've got M1 to M4, and then we've got T1 to T4. Now, notice here, we're reading from a buffer, and then we're writing out to a different buffer. And notice that we're sending it across the network. Now, again, this has to be generic. The model should be able to figure it out based on what my source and destination is here. The user doesn't have to put this. Of course, where I'm executing, the user does have to put it. So T1, it gets, it gets these two sensor data. And actually, we notice that M1, M2, we don't really need those because task 1 is the one that's reading these two sensors. So sensor data has been put into a local buffer, and we're using the same name as the sensor for the buffer name also. Once we're done, we're putting it M1 and M3. T2, it waits for M1. When it finishes, it generates M2 and M4. T3 requires M3 and M4, which has to fill both of those, and then it's terminated. T4, M2, and it's terminated. And then you can see each one of them where they process. This is the most important. The signals is where it's generating the data, writing it to some buffers. Okay, it's got certain rate, it's got certain size, it's got all of those attributes. Here, the tasks have its own rate, the message has their own rate, the task has its own rates. Right? And this is the message task time, which is the delay for processing. Now, one of the things on the messages is in this particular case, we were saying how much the delay on these different units. We got to be a little more intelligent. As Garo was mentioning earlier, it should be based on the size of the message and what is the capacity of the network, not just on saying, hey, it takes so many cycles. So we have to be a little more intelligent there. Of course, task time, which is fine. We just say it takes so many cycles. And then we have these, knowing what's your inputs and what are the outputs. So this is the database that has all the information about the message, the task. This one has information about the signals. And the third one is the routing table. Now, obviously, if we're using the node blocks or we're using our Ethernet block, we don't need this because we automatically will have the routing network topology. So, you know if it has to go from here to ECU1 to ECU3, we know exactly what the routing path is. We probably don't need that. So I'd focus on these two. The main idea here is to build a generic task graph modeling environment that encompasses not just this, but much more complex ones. So for example, if the model we're doing for 5G, data comes in, but depending on the data, I might break it down into 2 or 3 or 4 instances of this process in the first one. And then the outputs of those may go to 2, 3, or 4 other instances, or they may all go down to the same instance, or they may each one of them may spawn off like multiple instances. So can be any combinations of those things that we want to consider for doing task graph modeling. The key thing with task graph models today, all task graphs are done analytically, which means we compute, like how much delay it takes, and goes away. The problem with task graphs is system bottlenecks or deadlocks. What it means is, I have dependency for previous M1 to complete before T2 can start, but M1 is not able to complete because T1 cannot start up because the resource that it needs to process on is not available. So it creates an extended deadlock. This is what we want to be able to discover when we're doing task graphs. Where are my deadlocks? So this one here is a very good model. When I run this, we're not going to focus on all the statistics. We're just going to focus on a few of them. This one here is obviously a good one to tell me what my latencies are for the processing. And remember, we have that 20 milliseconds for worst case execution time. So this gives us a good idea of are we able to reach it or not. And right over here tells me where is my range. See, this one just puts all the point, but this one tells me my range. It goes between 0.6 and 1 point. So there are other kind of plots that I'm missing here. For example, the things that I would want to know is how, when the sensor data is generated and is put into the T1 buffer, how much time does it take before the data from the T1 buffer is taken out and to start executing the task? That will be your first question. So that's from ready to run to run. The other thing is you might have these things generated, but then it might wait on something else. So for example, Stencil 1 data goes to T3, but then T3 cannot start until T2 completes. So which means I have ready, but then only after the T2 completes, I move from ready to run. And from that point onwards, I'm waiting for a resource to become available, which is root of the problem of the T1 having a deadlock. And it takes some more time. So that becomes a queuing time. So it's a waiting time, a queuing time, and then the actual execution time. So I may want to split it up to see, where am I spending most of my time for each of the tasks. That will help me identify how much resources I need to allocate for each one of these. Okay? And remember, this can be done, as I mentioned, single board computer within a core, within process, across process on a board, or across in like a back plane in a single chassis to another board, or across a network to another distributed system. I can do all of these different things. So this here is a more of a task graph type template. So these are the three different types that I wanted to show you today. The first one was a very generic flow, which was really more of a software flow that's getting mapped to a hardware platform. Could be that some of them may have to be moved to hardware accelerators, but again, it's a very clean application flow. The second one was where more intelligence. I have sensors, I've got analog, I've got digital processing, I've got modems, I've got internet. So it's a very end-to-end. This one here is kind of in between those, which is more of a task graph, where there is a lot of complexity, but we want to be able to do it more textual as opposed to graphical. So this is the third thing that we would have. So we have three different ways of modeling these different types of systems. So now, based on this, we have to come up with a list of templates, and then we have to figure out how we're going to implement. Where, as Tom was mentioning, where do we add more details and where do we abstract them out? Now, notice a lot of the stuff already exists, so we might just be a question of putting them all together. Any questions?
Yeah, so I think that
Hey, Jimmy, are you still?
the behavior to architecture is a good concept that comes from Cadence. And Jimmy might remember some customers had untime models. They don't really aren't really amenable to what we try to do. But I do like what Tom said, where you have a kind of a simple flow and a complex flow. And so then the simple flow is actually a way to debug the model as well. So instead of all the details of the width and the speed, just have it 10 nanoseconds per whatever. And so then now the other thing you showed in the first model was the behavior was just a chain of things. And in reality, chains aren't really good because in today's systems, there's a lot of threads that are running. So there might be chains going across, but they might communicate with each other and they may trigger each other. So that I like. And I think that we would probably need to do the the architecture part. And so when it comes into the architecture, if it's, the detail flow, it goes one way. And if it's the simple flow, it goes another way. And so that's just a way to debug the model. The other thing I would suggest is any traffic or signal or sensor that goes in to the system, it has a deadline on it, set it to like maybe a microsecond or 10 microseconds, you could set it. And in the simple flow, if you get a deadline, and you check the deadline at the end of each step, then it would say you missed a deadline, and that probably means you have something that isn't connected, or you have so it's good that we can go down to the gate level or the decision in the software. But when you start building these things, it's sort of like you're assuming everything will work, and a lot we tell the customers to build them in subsystems and test them, but they never do, or very few do. And so I think it's better if we did the architecture blocks, and then we provide some of the behavior blocks, and the behavior, instead of going from left to right, it could also go up or down. And then I think you would have a much better thing. As far as the having the state flow diagrams, just have a separate model that has some simple blocks connected, and it generates the table essentially, that then can be entered into the to the other model. So then you do it in 2 steps. One, this is what I want to do, and then it generates what the bigger model would do, and then you put that as sort of a database. You'd write it into a database, and then the database of the traffic would pick that up and say, oh, I want to take this to this processor, or whatever I want to do. And I think that would be much better than the linear behavior.
That's a very good point, that not every system is going to have a linear behavior, and you're definitely going to have feedback loops and things like that. So yeah, I think we definitely want to take care of some of those things as well. So that's a good point. But as it all depends on the application, it really depends on what you're going to find for that particular application. If you find that it's just a flow through, it's a flow through. If you find there's feedback loops, there's feedback loops. So we just have to understand which one it is.
So some of the behavior could be software, and they could be different cores on the processor, and you might have something that in the behavior, does some kind of loading analysis and says, oh, go to this core or go to that core. And that core then would represent a thread of software.
And again, that would be something that the user could customize. That's where you saw that transfer, right? So you had them execute some stuff on one core, but in the behavior, we don't specify whether it's doing a core, whether it's doing a transfer on this particular bus, but rather we're defining that these are the sequence of things that are happening. Execute, transfer, execute, transfer. So it could be that the transfer is just going to another core on the same chip, or it's going across a PCIe to another processor, or it's going across Ethernet to another one. So the transfers will be that way, but you have to make it flexible enough that the user could set up whatever combination that they want.
Yeah, so I'll also point out that this one you're showing here has this, just the system resource. With the system resource external, you could actually put in a more complex bus protocol, for example. And So that's just the architecture blocks that you can have combinations of, you know, external system resource and a system resource, and then it could make decisions as to which, you know, what thread it wants to take. You know, even though you've assigned it to a core, it may use a different bus, for example.
Good point, Dale. Yeah. So, we start off with, as I was saying, the dashboard is something where they're moving from an analytical Excel spreadsheet model to a more discrete event, simulation-based, time-based model with concurrency. So there's a migration over there, and we want to make sure that we're capturing it. Now, of course, as Dale was mentioning, I could put the ECU. I can just make this a processor, put a bus, put some memories. I can add a lot of other logic to it as well as my next step. Matter of fact, Propel, if you remember the file that you were extracting, in that you will see there's ECU, and it'll say CPU, it'll say flash, it'll say memory. That's how they're defining what that particular hardware component is. Okay, so good. So why don't we start thinking about this, and then we start discussing, what are the applications that we can work on. So if each of you can start looking at trends and looking at what are the latest applications ongoing, I would say we'll start selecting from that list and coming up with here's a set of applications that we should target and go after this. I estimate that each one of these to take about a couple of weeks to get done. So depending on the application, it might take only 1 or 2 days, or the more complex ones may take 2 or 3 weeks. But that would be our goal in creating these templates. So one thing is, again, the purpose is anyone that's in that space, we just give them this thing and say, hey, here's something, you're ready to go. You don't need to know anything else. Here's your template for this application. Okay? Any other questions? Okay, thanks guys. Hey Tom, can you upload this to YouTube and send me the link?
Yes, sure.
Thanks guys. Bye.
Thank you.